control unit is a subsystem of the CPU which regulates the data movement within the CPU. It also controls data transfer between the CPU and the external memory and devices. The control unit also invokes the functions of the functional unit like arithmetic and logic unit when needed. It does it by generating a sequence of control signals on inputs which will see what inputs are needed. Now, to study the function of the control unit, let us revisit our instruction cycle from the very beginning and critically analyze what is supposed to be done. Okay. Now, let's see that the basic instruction cycle, as I've shown here, that an instruction is fetched, okay, and decoded, right? After instruction fetch is decode is over, it next comes to the state that it has to execute the instruction, and once the instruction is executed, it goes back into the instruction fetch and decode state once more. Okay, this goes on cyclically till we tell the machine to stop. Okay, now this is our basic instruction cycle. Previously, we have just elaborated a little bit in the case of our single operand machine, right? Say we take the instruction add memory y. That means it since it is single operand, we assume that it has an accumulator, and add memory y, it takes the content of memory location y and adds to the accumulator. Okay. Now, we have just elaborated a little bit more than the very skeletal state diagram that we have given here. That here we instruction fetch we do, then the machine decodes the operation. Now, get the operand address, that means it gets the address of that operand here. It then fetches the operand. After fetching the operand, it does this operation add, right? The result remains in that accumulator, as we said. Therefore, the store operand basically is a null operation here. Then it comes to the get next instruction once more, and the instruction fetch cycle, the entire instruction cycle starts once more. Now, this is a simple case. Okay. Let us elaborate it further and come to the general case here. Okay. Instruction cycle state diagram. We have shown it in a much more elaborated way because we need the actual operation that is involved to study what the control unit is supposed to do. Okay. Now, here you see that instruction fetch is here. Okay. After the instruction is fetched, opcode decoding is done, and after the opcode decoding is over, okay, operand address calculation starts. Now, here that we write operand address calculation because we have seen by this time there can be many addressing modes, okay, and many addressing modes, they may need the computation of the address, okay. And for example, say displacement addressing, based addressing, etc. It needs, okay, basically that computation of the address, though it is done hardware wise, but that hardware control operation has to be performed here. Okay. Now, one more thing that I should tell here, that all addresses that we talk over here are all addresses are in the form of that unsigned integers, so to say, okay, because you know addresses cannot be negative, therefore we tell this to be an unsigned, we take this to be an unsigned integer. Therefore, if necessary, that arithmetic operations in terms of unsigned integers that we discussed earlier will be useful here. Okay. Now, operand address calculation is done, and then request for operand is made with this transition to this state diagram, to this state. Okay, here we have that operand fetch, and if there is an indirect addressing, it makes a loop over here to get that operand. Okay, as many times an indirection goes. Mostly that indirection that we have discussed is one level of indirection. Now there can be multiple operands here. In the case of a multiple operands, that operand address calculation, okay, should be done once more, and the request for operand should be sent to the operand fetch once more. Now in the case of a two address instruction, it should be done twice, okay, and then after that operand fetch is over, it comes to the actual the data operation. Okay, now in the case of a data operation, when the data operation is over, that means some addition, multiplication, division, and whatever, or some logical operation, whatever is supposed to be, or even it can be simple move statements, okay, transferring of data. After the data operation is over, we come to that operand address calculation for storing the result. Here also there can be indirection, and if necessary, that indirection step is taken. That means address is fetched once more from the memory, right? Only then the address of the operand is available. Then the operand is stored. Now, up to this, that instruction execution is over. Now, after this, if there is some external stimulus, like say interrupt, okay, for example, that the CPU earlier told the some IO device to do some operation. Okay, on completion of that operation, the IO device may interrupt the CPU. Then the CPU will in fact check whether there is any interrupt or not at this point after that instruction execution is over. Okay, if there is an interrupt, then the CPU should process the interrupt. If there is no interrupt, then it comes over to here. On processing the interrupt also, the control comes back over to here, and then we go for instruction address calculation for instruction fetch once more. Okay, and the entire cycle continues. Now, to see that at every steps, okay, like instruction fetch, then operand address calculation, then operand fetch, etc., what micro operations are involved. Okay, let us see how actually these operations are performed. When you say that what micro operations are involved means that all this which has been shown in the box in terms of a state needs many smaller functions to be performed, many smaller operations, sub operations to be performed, in terms of which the bigger operations is broken down. Okay, these are called micro operations. Let us see what micro operations are involved at every step. Okay, let us see first that the fetch cycle, what kind of data flow is involved. Now, the fetch cycle, the content of the program counter should come to the memory address register, because the program counter points to the instruction that is going to be executed now. Okay, therefore that has to be fetched, and therefore whatever we have to fetch from memory, the address of which should be in the memory address register. Therefore the program counter content is transferred to the memory address register. This is controlled by the control unit once more. Okay, right. Now, memory address register address is sent to that address bus. Control unit sends signals to the control bus, which tells the memory that a memory read cycle is involved. On getting that, memory takes the data from the location pointed to by memory address register. That data is passed on this data bus, and from that data bus, the data comes to MBR, which in fact is the instruction here, and that instruction is now sent to instruction register for decoding and subsequent operation. Okay, that is when we talk about a fetch cycle, right? Now, let us say if we talk about a situation where we possibly are executing an instruction like this, okay, let's say move content of R5, I mean move the content of memory location pointed to by R5 to R2, okay, say this is the operation that is involved, right? In that case, let us see what are the basic steps that is involved to execute this instruction of transferring the content of memory location pointed to by R5 to R2. Now the content of R5 has now have to be switched into that memory address register. Then the content of memory address register should come onto that address bus. There should be a request for read to the memory once more. The data at the location given by the address bus will be thrown into the data bus. The memory will say through the control bus once more, right, the data is ready. Then from the data bus, the data should be channeled into or MBR, the memory buffer register, and from there the data should be channeled to R2. Okay, once more you see there is a memory read cycle that is involved over here. Now, if instead of the operation being move indirect R5 to R2, if the operation is move R2 to R5, that means the content of R2 to indirect R5, it means that the content of R2 should be written into the memory location pointed to by R5. In that case, the steps would have gone this way, that R5 content should once more be put into the memory address register. Then a control signal says that write memory instead of read memory. Okay, because now the data is in R2, which should be first transferred to that MBR. From MBR, the data should come to the data bus. Therefore, this data flow, this direction should change R2 to MBR, MBR to the data bus. And from there, the memory would have taken the data and would have written into the memory location, which is given by this address bus. And on completion, it will send the signal to the CPU that the data has been written into the memory. Okay. Now let us see. Let us take another example. Okay, where that we are talking about that indirect cycle, right? Now, in the case of an indirect cycle, let us see what happens. Let us take an example. Say we say that to move, say to register R3 content of memory location, say not content of memory location pointed to by the content of memory location log, because this is an indirect addressing, pointed to by memory location log, that has to be brought into R3. Now, in terms of our machine that we are talking of, that this will have a instruction like this, that it should say that move R3 is a destination. Then it should say that the mode should say that it is an indirect addressing involving memory, and here the address of the location, that means location address, is in the next word of the memory. Say this is in location 700. We assume that this word is in 702. The program counter is now pointing to here because this instruction is being executed, and when this instruction fetching is over, the program counter will be incremented by 1, we said, okay. Basically, the program counter will be incremented by 1 or 2 depending upon the word size. If we say that its word size is the entire word, then we can say the program counter will be incremented by 1, and we say that this address is 701, okay. In any case, the program counter will be incremented to the next word, okay, and now the program counter is pointing to the address pointed to by program counter is pointing to the address of the memory location from where the address of the actual operand has to be fetched. Okay, let me repeat. Then the program counter is pointing to the address of the memory location, okay, from where the address of the actual operand has to be fetched. Okay, now this has to be done this way. Therefore, in 2 steps. First, the program counter should come to the memory address register. Okay, right, to get the content of the memory location lock. Okay, content of the memory location lock. The content of program counter, which is the address of lock. Okay, content of program counter, which is the address of lock, should come to the memory address register. It is not an instruction fetch cycle, it is essentially operand cycle, right. That address now is thrown to the address bus. A memory read operation is initiated. Memory reads the content of the memory location log and sends it to MBR. Okay, say this is lock. The address of lock is now in that MBR, and say this lock now contains say 500, say 5000. Okay, therefore the actual address of the operand is 5000. The operand has to be fetched from here. Therefore, whatever has now been fetched from the memory, which is comes to that MBR, which is 5000 now, okay, should be sent back, channeled back into the memory address register because indirection is involved. That address 5000, okay, is now thrown into that address bus. The data is collected from the memory because once more a memory read cycle is initiated, data is collected from that memory, and that data comes to that MBR. Only then the operand is available at MBR. Now, if this operand has to go to R2 or say, then this has to be now channeled into the corresponding register that has been told to be the destination, which is R3 over 2 here, which means now instead of that MBR going to our IR instruction register, it should be content of MBR should be channeled into R3. Okay. Now this is your, what should I say, that indirect cycle. Whenever there is an indirect cycle, as you can see, that one more memory read turns out to be involved, or it may be a memory write if the operand has to be written into the memory. In any case, one more memory cycle turns out to be involved here. Okay. Now you can see in that case that basically there is a function that is needed which will transfer the data, will move the data from register to register. Therefore, let us study that how we can make an arrangement for moving data from register to register. Okay. Let us take a simple example and show this situation. Here, what we have taken is this, that we have taken say 3 registers, so to say, RA, RB, and RC. Okay, these are the three registers where the data can be done. Each register has an input lines. Okay, we have shown one line. Actually, it is as many lines as the breadth of the register. That means as many bits this register is the register can hold. That means the width of the register is the number of bits the data consists of. Okay. Now, RA, RB, and RC, each register has several input lines, okay, and several output lines depending upon the size of the register. Now, each register is connected to the other register. For example, you see that RA output is connected to input of RC, and RA output is connected to input of RB, and so on for RB and RC also. This we call data paths, and every data path, say here and here, we have kept gates. Okay, C1 is a set of gates for each line in the in. Okay, each line in this data path. If it's 16, therefore 16 such gates are there. Okay, now C1 is the gate which, when open, only the data that is available can come into RA. Similarly, the C2 is a gate. Okay, when this is open, the output of RA can come into these two lines simultaneously, right? Now, suppose that we want to move data from RA to RB, right? Let's see what have to be done. The gate C2 has to be open so that data is available here, right? And after the data has come, the data stabilized, the gate C3 has to be open so that data can come into RB. Okay. Therefore, if we say that I want to execute an instruction of the form that move register A to, say, register B, the operation that actually is involved, that you open gate C2 and gate C3, all other gates should remain closed. Therefore, basically we say that make C2 1, C3 1, and leave all other gates at the 0 level. Okay, then we can move RA to RB, not R3. It is, oh sorry, black pen. Move RA to RB. Now, similarly, so for example, if you want to move, say, RC to RA, okay, say move RC to RA, the gate that will have to open is, that will have to open out of RC is C6 and into RA is C1. Therefore, C6, C1 you will have to open, right? That means C6 should be 1, C1 should be 1, other should be 0. Now, if we want to sequence, that means if we want to now execute these two instructions one after the other, that means move RA to RB, then move RC to RA. In that case, we'll have to first open the gates C3, C2, then have to open the gate C6, C1. Okay. In that case, the content of RA will be transferred to RB first, and then the content of RC will be transferred from, say, from content of RC will be transferred from RC to RA. Okay. Now, another important thing that we can see here is that, say, we want to move the content of RA to RB, and we want to move simultaneously the content of RD to RE. Now, since these two data paths are totally mutually exclusive, we can say at the same time open this gets say C8 and C10, in that case the data of RD, okay, will come into RA. Therefore, say move RA to RB and say move RD to RA, this can be simultaneously performed by opening gate C3, C2 and gate C8, C10 simultaneously, and possibly we can name this say move double RARB RDRE as if it is a single instruction. Now the point to note here is this, that what happens actually, that if we want to move information from one register to other register, we create a data path, keep a data path from register to register, but depending upon that from where to where we want to transfer, we open some control gates. Okay, and we also open these control gates in time sequences. For example, if this have to be done first and then this have to be done second, then say possibly we do it at the T1 time instant this one and T2 time instant this one, T2, okay, where T1 is in less than T2, okay. And to do these operations, we can keep a clock, and that opening or closing of these control gates are done in synchronism with the clock pulses. Here, all these gates that controls the data movement from register to register has been shown in terms of readings and marked as C1 to C10. Okay. Now this is a general picture. What we can have from here is a picture of a control unit, right? You see that the control unit, this is our control unit. It has C1 to C10, the control lines. It has an input clock, right? The output C1 to C10 is activated in terms of the clock pulses. For example, we can say when the clock pulse is high, then these control signals are activated. Now, which control signals will be 1 and which control signals will remain 0, that is determined whatever we have in the instruction register. Now, the instruction register will contain therefore that instruction say move RA to RB, move RD to RE, move RC to RA and so on. This instruction should be in the instruction register. Therefore, at any point of time, depending upon the content of this instruction register, the control signals are generated from this control unit, okay, in synchronism with the clock pulses to open or close these gates in the data path so that the data movement accordingly can take place. Okay, this is in fact the crux of that entire data flow movement within the CPU and as also between the CPU and the external device, as we will see. Okay. Now, one important thing is here. One important thing is, say here we have only 3 registers, and immediately you can see that we have to have 6 lines so that each can be interconnected with the other. Here another 2 pair of registers is there, which is independent of this set of registers, and 2 lines are needed so that informations can be exchanged between these 2 registers, right? Which means that if we have, say, in a group that n registers, okay, and we want that any registers should be able to transfer data to any other register, then we will have to have the number of lines, total number of data paths 2 into NC2 or n into n minus 1. Basically, we will have to have n P2 lines, data paths that should be available, interconnecting each with the other. Now imagine that, so for example, if it is 10 registers are there, in that case there will be 90 such data paths that has to be available, right? Imagine the situation where you have say 64 and more registers are there, and we want that content of any register can go to any other register. Then it will be basically a jungle of data paths, and so much of data paths cannot be afforded. Okay, then what can be done, right? So that the content of any register can be transferred to any register. A very simple solution exists, and that is this, that we keep what we call say a bus, okay? And say we have register, say RA, register RB, say RC, RD, RE, and so on. What we do that say this is the inline of RA and this is the outline of RA. Okay. Similarly, say this is the inline of RB and this is the outline of RB. Right. Similarly, we can have here and we keep our control signal gates, control gates here, okay? Keep it, show it here rather. Now you see, if you want to transfer from RA to RB, what you do, say let's name them. So this is C1, C2, C3, C4, C5, C6, right? Say C7, C8, C9, C10. Say we want to transfer the content of RA to register RC. Then what we'll have to do is that you open C2 and open C5. The rest remains closed. Okay, that means make C2 1, the control point C2 1 and C5 1. Then RA will be now gated into this, say, data bus. The content of RA will be gated into the data bus, and that information, that data, will be channeled into RC. Therefore, you can see that if you want to transfer any information from any register to any register, that from register should channel the data into the internal bus, the data bus, and the two registers should take the data from the data bus. Okay, and depending upon from where to where we want to transfer, okay, the control unit should open the gates accordingly. Okay. Now, one of course important thing remains that if we have to transfer parallelly, say information from RA to RB and RD to RE, in such a situation this will not be permitted, because only one register can get its data into the data bus, and more than one register, one or more registers can of course take the data into it. Therefore, from one to many we can send the data, okay, but parallel independent transition, like say we are doing RA to RB and RD to RE, cannot be done here. which means that sometimes will take some more time to transfer a total amount of information from a set of register to a set of registers. We may have to sequence them properly so that the data transition from register to register is done in a non-error way. Okay, that means without interfering the information or the data of one register with the other register. Okay. Now, let us come back over to this. We call this one is our control unit, and such a unit should be there within the CPU. Okay. Generally, we are assuming here that this is a hardware circuit. Basically, it will be what we know as a sequential circuit. It will go on generating sequence of control words from C1 to C10, taking that entire combination of bits. We take a control word. It will go on generating a sequence of control words in synchronizing with the clock pulses, depending upon the what input we have here in the instruction register. Okay, and as we said already, that to reduce the number of interconnections amongst registers, we use a data bus for transference. Let us look the situation. Look into the situation inside a simple CPU. Okay. Here, the internal data bus has been shown in red. Okay. Let us recall the original simple diagram of the CPU that we had shown earlier. You see that we have several registers: accumulator, a temporary register, an instruction register, a register bank here, the program counter, the address buffer. This is the memory address register, the data buffer, which is the memory buffer register. This was the control unit we showed. No others control signals were shown that time. Only it was showed that decoder should tell that what the arithmetic logic unit should do, and the control unit should invoke the operation of that arithmetic and logic unit when the time is ripe. It's needed that the ALU should be invoked. Okay. Now, this picture, in terms of the discussions that we have right now, can be elaborated here. Okay, as has been shown in this diagram. Right. Here you see that this is our internal bus. Okay. We had the internal data bus here. Okay. Right. Here is a register bank. We can have the information for the register bank into the data bus, or the data from the internal data bus can go to the register bank. Now, let me elaborate this a little bit. Now, this register bank, which are inside the CPU, okay, are there so that the fast access to the registers can be done. And therefore, what is done is this, that these internal either general purpose registers or data registers, they have their own multiplexer, and any information from any register to any other register can be done, okay, without involving the internal data bus altogether. Which means that, for example, if you want to transfer R1 to R2 or say R3 to R4, that there is a multiplexer which will automatically take the input from R3 and load into R4. Okay, and that is done very fast, and it is needed, it is required, and we need that this be done very fast, and therefore there is a multiplexer circuit through which the data transfer takes place within the register bank. Okay, we will be assuming this picture over here. And in most cases, most CPUs, the general purpose registers, do exchange data that way only. Now, here is a memory address register. The address comes from that internal bus into the memory address registers, and the address lines goes. Now, where we have shown by means of a single line, actually there are many lines depending upon the width of the data word. Okay, it may be 16, 32, 64. Okay, depending upon what machines you have, 16-bit machine, 32-bit machine, or 64-bit machine. Okay. Now, for the data, for the address, how much width that memory address register will have depends upon how much memory you can support. We'll discuss it when you come to the memory organization. Now, let's see, let's complete the discussions that we had. That here we have a channel from internal bus to the memory address register, and that's external bus. The memory data lines are bidirectional, therefore we can have that data can be transferred from internal bus to MBR and from MBR to internal bus. From the memory bank, content of any registers can be thrown into the internal bus, okay, or from the internal bus, the content of the internal bus, okay, the status of the internal bus can be put into any of the register, can be loaded into any of this register, okay. That content or the status of that internal bus, which is containing essentially, so to say, a data, right, can be channeled into instruction register. It can be channeled into program counter, or the content of program counter can also come into the internal bus. It can be channeled into a temporary register, say T, or a register A, which can be used as an accumulator if one wants. Output of the arithmetic logic unit is also can be transferred to that internal bus. The control points are here, that say here, that instruction registers opcode will come, that add or subtract or multiply, that ALU should perform that. At every point there are control gates, okay, with control signals operating, actuating them. So C1 is a control signal for this gate, and so on, right? Now, that is the situation of our internal memory organization. And you can see that we have taken, so to say, a rather simplistic view. We have shown only few registers that are involved here, okay, that are needed for our discussion, okay. But you can see that if there are more than registers that are shown over to here, that also can be accommodated within the same framework of discussion that we are having, right? Now, with this structure specified, okay, and that mode of data transfer between the register and register understood, we should now discuss that how the instruction cycles, the instructions are fetched, the operands are fetched, and the instruction is executed, okay. We'll discuss it in the next class with this structure, that actually how the control signals should operate these gates so that the operation that an instruction tells, okay, or instruction specifies is carried out, okay. Till that time,